Okay, so this is a talk on scalable machine learning approaches for neighborhood classification. And the authors are Manu Sethi et al. From the University of Florida in the Maine. Before we begin, we wanted to apologize for the perfect storm of problems that resulted in none of the authors being physically present in Sydney due to a combination of travel, health issues, and bureaucrats with a passport fetish. None of us were able to physically be present in Sydney, and we apologize for that. Okay, so let's just go over the basic outline. In a sense, this talk is going to focus on the problem of labeling pixels in slums and other informal settlements in various parts of the world, not just in the third world. It's also going to involve certain cities in the United States. The talk is going to essentially comprise a few parts. We're going to cover the limitations of previous methods. We will then describe our approach in significant detail, highlighting in a sense where we differ from the previous methods, and then offer some results and ideas for future work. Before we begin though, we would like to mention that one of the principal contributions of this work is essentially a synthesis of computer vision based segmentation methods with machine learning driven classification methods being put together into one coherent framework. And that's hopefully will come across as we proceed. Okay, so let me just give you a quick background into the problem. At present, the proportion of population living in slums worldwide is actually increasing, and this is partly being driven by obviously an increase in world population. It's also being driven by the fact that urban demographics are being skewed towards more people coming in from rural areas in search of jobs, and this, when combined with climate change and other types of potential disasters, makes these kinds of informal settlements even more vulnerable to disasters. So it would be useful to be able to label regions of urban areas as well as other areas as slums or informal settlements, and be able to separate them from remote sensing imagery. And this is essentially the goal of our work. Okay, so take a look at the picture shown on the right, which loosely separates an urban region into formal versus informal settlements. And you can see immediately that it's a challenging problem to be able to identify informal settlements from remote sensing or high resolution satellite imagery. And the main reason is that the spatial pattern, while it may look different across categories, significant amount of image processing, computer vision, and machine learning methods are going to be needed to be able to do a good job to separate these regions, as is shown in this figure. Okay, so now before we really get into the nitty-gritty of the distinctions between our method and previous methods, we want to mention one overarching difference which we think is important, and that is that we are not going to think of our problem as strictly as a machine learning problem. In other words, there's a tendency among a lot of methods to jump into these types of pixel labeling problems and simply think of each pixel as being an independent feature, and then given a set of training samples to then go ahead and label the pixels into different categories. What that does, unfortunately, is it does not take into account the fact that pixels are highly correlated, and therefore you can imagine that several pixels essentially form a larger coherent region, which first of all is perceptually visible, but also is something that machine learning methods should take into account. So the defining point of departure of our method from previous methods is that we are going to focus first on image segmentation, and that aspect of image segmentation is going to be largely unsupervised, where we will take images obtained from satellite imagery and then essentially segment them in a hierarchical scheme such that there are coherent regions that emerge during that process, and those coherent regions are then going to be processed further to produce features which are then input into a semi-supervised learning algorithm. And that's going to be the pipeline of our particular approach. Okay, so having given you the basic idea of the pipeline, we'll just formally now go through what it is that we do. We first tessellate our input images into superpixels. Superpixels are basically these coherent regions, local coherent regions, where you can imagine that there is a particular object which looks coherent from a visual inspection. We're hoping to produce that via unsupervised image segmentation. These are going to generate multi-pixel features in each superpixel. These superpixels are then going to be initialized using certain expert labels, and then a support vector machine is going to be used to then label initialization of these superpixels. A superpixel graph is then going to be constructed for further label refinement for semi-supervised learning, and that's essentially going to be done using a Laplacian graph propagation step, which will become clearer as we proceed. Okay, first. So the basic idea of tessellation is that we would like to parcellate the image into coherent regions. This is, in our opinion, significantly better than using regular grids, because regular grids do not take into account the local coherency, spatial coherency that is seen visually when you inspect these images. And what you can imagine is that there could be in certain regions certain superpixels that are small because the coherence is at that small level, but in certain other regions where there's a lot of spatial homogeneity, you can imagine these superpixels to be fairly large. It's this type of image segmentation that our method is going to leverage, which you do not see in other methods that use regular grids. Now, this results in a huge reduction in data complexity. In particular, we are going to use the ultrametric contour map, which is a particular kind of image segmentation method. We're going to leverage that in our pipeline, and this will become clearer because we're going to actually walk you through how the ultrametric contour map is actually used in our work to produce the superpixels. Okay. So what is UCM, or ultrametric contour maps? It's considered to be the state of the art in 2D superpixel estimation, though we have to qualify that by saying that that's only done on certain data sets like the Berkeley segmentation data set. What it basically does is, rather than just use local features to produce image segments, it actually combines local and global cues using perceptual organization, and it also computes gradients at different scales and orientations to produce the local cues. So in a sense, you have global nature coming in from two different ways. One is via different scales and orientations, and the other one is through perceptual grouping. And how is that done? Well, you construct a feature vector at each pixel. From the feature vector, you construct a weighted graph. The weighted graph is then fed into essentially a spectral clustering or a spectral decomposition method, from which you obtain eigenvectors. Those eigenvectors are then turned again back into global cues, which is then further fed into a feature processing framework, followed by a watershed transform to then obtain the final segmentation. Okay, so what this results is in an image segmentation, which is unsupervised. It also produces a hierarchy, of course, to find segments. So what you can imagine is that when you run UCM, you don't just get a single set of superpixels, you actually get multiple sets of superpixels with containment across the hierarchy. Different neighborhoods often get classified better at different levels of the hierarchy. So basically what we're getting is a hierarchical parcellation of the image at multiple levels, with the expectation that different neighborhoods are going to essentially pop out at different levels of the hierarchy. For example, at very coarse scales, UCM is able to, as we will show you, separate out urban regions better at the coarser scales compared to the slums, which may not necessarily show up at that scale, but may show up in a different scale. This work is actually from Arbelas et al., contour detection and segmentation in PAMI and in CVPR a few years ago. Okay, So take a look at the two images on the left and the right. We are showing superpixels obtained at coarse scales and superpixels obtained at fine scales, without necessarily getting too much into the nitty-gritty of superpixels here. Just notice that the urban boundaries are clearer in the image on the left, and you can see on the image on the right, you can see that there are a lot more boundaries available. In particular, the informal settlement boundaries are actually starting to show up, and in the finer scales. Clearly, this indicates that very rich features can be obtained by combining information at multiple levels of the UCM hierarchy. Okay, so what do? We essentially generate multi-pixel features, which is a nice advantage of our method, because a superpixel is going to contain multiple pixels, and we are able to then leverage the fact that multiple pixels are contained to produce multi-pixel features like intensity histograms, average RGB values, corner density, and etc. And in a nutshell, what we do is we weigh these features and concatenate them to produce a 58-dimensional descriptor for each superpixel. Now, I don't really want to take you through exactly how this 58-dimensional descriptor is actually built up. For further details, please take a look at the paper in the proceedings. But essentially, what is going on is that the superpixel, by having multiple pixels in it, is able to produce a 58-dimensional descriptor. Okay. Of importance in this descriptor is the corner density. The corner density turns out to be quite a useful feature for urban and slum regions, but as you can imagine, is not such a very important feature for forests. We also have these binary valued features, which allows us to pick up different regions at different hierarchical levels of UCM. And so the basic idea here is that you get the stronger boundaries at coarser level of tessellation in UCM, whereas other regions get put into bigger superpixels as you go through the hierarchy, and that allows us to produce binary valued features which can separate between these two types of classes. Okay, so the two images show you the binary urban descriptor and the binary slum descriptor, and without necessarily elaborating this too much, you can clearly see a separation that is created by this binary urban descriptor by deriving coarse scale UCM features and multi-level superpixel containment features respectively for urban and binary and slum. Okay. So now let's go through the semi-supervised learning approach. So far, we focused mainly on image segmentation and on feature extraction and the descriptor at each superpixel. Basically, what happens is that in semi-supervised learning, you can imagine that only a very few pixels are going to be labeled by the experts. So because of this, we essentially have very sparsely available ground truth data, and what we do is we have considered different types of methods, k nearest neighbors based on KD trees, and support vector machines with just a linear kernel. And the idea is that now that we've got a descriptor that's actually not just individual pixel based, we can afford to run a machine learning method and then proceed to see how well it's able to leverage the initial set of few pixels that were provided. Okay. Now, the first stage support vector machine only produces rudimentary labels. It might still have artifacts where different regions belonging to the same class may have different labels. So what we do is we then use a Laplacian propagation after the SVM to smooth the labels in the previous step. So in a nutshell then, the overall process can be summarized as an image segmentation step followed by a feature extractor which gives you a 58-dimensional feature, and then that's followed by SVM, followed by Laplacian propagation to smooth the labels resulting from the SVM. Okay, so how do we do this? Well, the nodes of the graph are superpixels. The edges of the graph connect adjacent superpixels in the spatial domain. In this way, the fact that there's a spatial metric is leveraged with the graph. So the spatial graph is actually marked on the image that you can see on the left. Now let's take a look at the Laplacian propagation. In the Laplacian propagation, it's objective function c of x, which is given on the slide. The main point of note is that the xi, which are the labels that we want, are actually real valued. And what we will do is, after having minimized this objective function with respect to the xi for each category used, we will essentially do a winner-take-all to produce the final label. So what this basically says, this objective function is basically saying, is that you have an initial set of labels yi, you want to find a new set of labels xi with a term which essentially comes from Laplacian graph label propagation, which is the first term in the objective function. And there's a weight vector, a weight matrix wij, which is based upon the pairwise distance between features which are used. Okay. So the Laplacian propagation, because it's fairly simple, and because if you looked at that objective function, it was actually quadratic, it results in a linear system, and the linear system of equations can be very efficiently solved. And this is actually taken from previous work by Angelova and Zhu in CVPR 2013. Okay, so since I'm running out of time, let me just speed up. The images shown here are just the fact that when you define neighborhood labels, the Laplacian smoothing is able to improve upon the preliminary classification of SVM. The next slide shows the experimental results for Rio, Brazil. You can see the actual image, the preliminary classification, and then the final result. Again, this is another result from Rio, Brazil. And then here is a picture of Detroit with the categories shown being undeveloped, commercial, residential, and forest. The image sizes and other categories are shown here. What we do is we do the same thing, preliminary classification followed by Laplacian smoothing. And again, I'm running out of time here, so what we will do essentially is just show you quickly that we have similar kinds of results for Madison, Milwaukee, USA. To summarize them, take a look at the classification errors. You'll see that we've executed this method on Rio, Madison, Milwaukee, and Detroit. So it's not just Brazil, but also United States. And you can see that as the percentage of label data, particularly in Detroit, as it goes down, the misclassification error actually goes up. But basically, the misclassification error is an indication of how much we have to still improve. We want to point out that the misclassification is error, considering that the amount of label data is only 1 or 2%, is, in our opinion, may even be acceptable in certain commercial applications, though we will have to wait and see if that is borne out. The other experimental results, basically these are comparisons. You'll see with previous work with GMIL that in the main we improve on for Rio, Madison, Milwaukee, and Detroit, with the percentages on the right being seen to be lower than the percentages on the left in terms of the error on superpixels from the proposed method. So this indicates that relative to a previous method, which has been quite popular in the community, we seem to be doing better, at least with respect to these images. So to conclude, we essentially brought superpixel image tessellation via ECM into the problem of semi-supervised learning, and to be able to separate urban and informal settlements. We evaluated it on 3 different geographic settings and showed good classification performance. This work can be extended to temporal data, which is something we're actually doing at the moment, and we hope to be able to do further work exploiting the hierarchical nature of UCM to get contextual level selection and to be able to improve upon our present work. Once again, we apologize for not being able to be present in Sydney in person. It was due to no fault of ours, in the sense that there was a perfect storm of problems, but we hope that we've been able to communicate our work in a fairly effective manner. Thank you.
Okay, so let's give a round of applause to our remote speaker.